Okay, today I'm coming to you from my home office with special guest classmate Ellie. Ellie. She's here to simulate the classroom environment. So let's start Lecture 4 with a brief recap of Lecture 3. We reviewed equilibrium, particularly this concept called the equilibrium constant, which expresses the relative concentrations of all species at equilibrium. We do not bother including solids and liquids in the expression. We went over why that is in Lecture 3. We also went over how gases and aqueous species work in this K expression. For gases, we use units of bar, which is actually a unit of pressure, but pressure and concentration are directly related to each other. And for aqueous, we just use units of molarity. Despite the units above, the K value itself has no units. The reason why this is more of a pChem idea. And then we just learned a generic way of expressing the constant, which is just concentration of all products of an equilibrium raised to whatever their coefficients are, divided by the same concept, but for reactants. We then covered a specific type of chemical equilibrium in which we described the solubility of a solid in water. And so in this type of equilibrium, a solid in water dissociates into its constituent ions. And then these ions start reacting together to reform solid, and an equilibrium is reached. And the equilibrium constant for this type of reaction has a special subscript that stands for solubility product, in other words, KSP. And from this value, we can determine the solubility of the solid, which is defined as how many grams of solid dissociate in 100 milliliters of solution. And we went over the math behind this, but let's recap that as well from a slightly different perspective than in Lecture 3. So let's say we have this solid rock of SRF2, and initially we have 4 moles of it, but let's express that number to 5 sig figs worth of accuracy. And that initial volume would be 0.11850 liters. And so we can calculate that initial concentration by taking moles and dividing by liters, and we get this large concentration of 33.753. It's not surprising that it's large. Solids and liquids are densely packed with atoms. So now let's drop the rock into some water, and let's say the resulting solution is 1 liter in volume for simplicity. And we can see that some of the rock has broken away. It's dissociated into its constituent ions in solution. And so, to determine how much of that rock broke away, which describes the solubility, we make the following statements. Using the math that we learned in Lecture 3, we can calculate that the final concentration equilibrium of SR2+ is 8.6 little 6 times 10 to the minus 4 molarity. Well, that means that in this 1 liter of solution, fucking hell. What a shitty program. Well, that means in this 1 liter of solution that 8.6 little 6 times 10 to the minus 4 moles of SR2+ were formed. Well, in turn, that must mean that that same amount of moles of SRF2 were used up, because it's a 1-to-1 relationship over here. And so if I take the number of moles that were used up and subtract it from our initial moles present, we will get the final moles of SRF2. So it's gone down a little bit, and that agrees with what was stressed in Lecture 3. The objective amount, the moles or mass of a solid absolutely do change over the course of a reaction. But while we lost moles, we also lost volume, and so volume has also decreased. When I take the final moles and volume of SRF2 and divide them by each other, I get 33.753 moles per liter, the same as before. It's the concentration that does not change, and that's a very important distinction for you to remember. Another important distinction to remember is the difference between the concentration of SRF2, the solid, and the solubility of SRF2, which both use units of moles per liter but describe different concepts. The solubility refers to the moles of SRF2 that were dissociated, not that are remaining, but were dissociated per liter of solution that the solid was put in. And from there, we just take those moles per liter and convert to grams per 100 milliliters. And we went over that math in the last lecture. And so one final little note about this. Last lecture we discussed the significance of K size. We're just going to add one more part, and it's that note in blue at the bottom. A higher KSP means more product is formed, thus the solid reactant is more soluble. And you can see that that agrees with the math of this K expression here. Larger K, more product. Well, that means more reactant must have broken apart. And so that's solubility. And now, before we move into Chapter 8, which is our main focus for the day, we're going to quickly jump all the way to Chapter 12.3. I know it seems crazy, but we do get a very useful tool for equilibrium out of this. So the concept we're about to learn about is called a charge balance. Let's write that down. Charge balance. And what this principle states is that the total positive charge must equal the total negative charge in solution. Total positive charge must equal total negative charge. Must equal total negative charge in solution. In other words, we need electroneutrality. Electroneutrality, not the last time we'll see that term, but it just states that there's a charge balance. And so to understand what we just wrote, I'm going to show you a couple of visual examples and then we'll write some important notes down. So imagine that we have some solid NaCl, and this is a very poor representation of what solid NaCl looks like. But just imagine a bunch of those atoms clustered together. And we'll say we have 4 moles of it, and we're about to dump it in solution. Well, NaCl is a strong electrolyte, so it will 100% dissociate into 4 moles of Na plus and 4 moles of Cl minus. And so the reaction that just occurred was NaCl totally broke apart into 4 moles per liter of each of these. And so this solution is charge balanced because we have 4 moles per liter of this positively charged ion, but we also have 4 moles per liter of this negatively charged ion. So the two balance each other out, and we have electroneutrality. Let's do a slightly more complicated example, this time using barium nitrate, still 4 moles. It dissociates, but because there are 2 NO3s in each barium nitrate, we get twice as many nitrates as barium ions when it breaks apart. And so this just happened. And now while the ions do not have the same concentrations this time, the solution is still charge balanced. Because if we do quick dimensional analysis, we can say that while we have 4 moles of barium ion per liter, every mole of barium contributes twice as much positive charge. And so our solution is still, in fact, charge balanced because we actually have 8 moles per liter of positive charge total, perfectly balancing the 8 moles per liter of our negatively charged ions over here. So next I'm going to write a mathematical equation that describes charge balance. And first I'm just going to write it, and then I'll define what everything means. So let's just get it down first. Charge balance equation, EQ for short. And it'll be lowercase n subscript 1, concentration brackets, and then capital C subscript 1, plus, and then we'll write the same thing, but this time we'll put a subscript 2, and then we'll write dot dot dot. And then we'll say equals, and we're going to write something very similar, but this time we'll use lowercase m, subscript 1, concentration brackets, A, capital, subscript 1, plus, write the same thing again, but give everything a subscript 2, and then once again we'll do a dot dot dot. Okay, so what the lowercase n represents is the charge of our cation. And the other part represents the concentration of that cation. And in those visuals we just went over, it was very simple. We always just had one cation and one anion. But in more complicated solutions, there might be more than just one cation. That's why we have these subscripts like cation 2, and then there might be a third cation or a fourth or a fifth, and that's why we wrote the dot, dot, dot. Then on the right side of the equation, we have very similar symbols. The lowercase m describes the charge of some anion. And this describes the concentration of that anion. And once again, there might be more than one anion in solution, and so we label each one with a different subscript. So if we were to apply this equation to the previous slide, slide 7, where we had barium nitrate, NO3, but 2 of them, totally dissociating into barium 2 plus and 2 separate nitrate ions. And so the charge balance expression for this solution would look like this. We'd have some concentration of positive charge coming from these Ba2 plus ions. Let's not worry about the coefficient yet. And that must equal the total negative charge coming from these NO3 minus ions. And so now we toss in the coefficients, which again are based on what the charge of the ion is. And so barium has a charge of 2 plus, so the coefficient we put in front of it is 2. Whereas nitrate has a charge of minus 1, so its coefficient is technically 1, although of course we don't need to write that. Notice we don't include the negative sign, because we're talking about concentrations. They should be objectively positive. So it's like I'm taking the absolute value of that charge. Now this is the part that's very counterintuitive. After all, in the chemical equation, we see the 2 in front of the nitrate, so you would expect the 2 to be in front of the nitrate in the charge balance equation as well. But in fact, the 2 goes with the barium, and that does make complete sense if we really think about it. So there's 2 ways to look at it. We can think of it as, for every barium ion, we need twice as much nitrate to balance the charge. Or we can think of it as, every barium ion contributes double the positive charge, which needs to be balanced by those nitrates. So the last thing I'll show you in this video is that slide 9 does have a clicker, and it's about a charge balance for a much more complicated solution, but that can be expressed using that same formula that we just went over. We'll of course do this in Zoom.